Hello, welcome to 7.2, day 1. Today we're going to learn about means and variances of random variables. Now, we're going to start out with a probability distribution, and we want to find out what the average payout for this lottery is. In order to do that, what we do is we have to multiply these, our x variable, and our probability. So 0 times anything is 0. 500 times 0.001 is 0.5. Now if we add up these values, which will just be 0.5, this will be the average payoff for the lottery. Now obviously nobody in the lottery will get 50 cents. 0.1% of the people will get $500, and most of the people will get $0. But the average payout is 50 cents. So what that means for people who are setting up the lottery is they have to charge at least 50 cents in order to break even. And anything above that will be profit. Now this mean is not the mean x bar because we're not taking an average of a set of data. This is what we'll call this mean mu. Now we use Greek letters for more theoretical values in statistics. We call them parameters. We'll get into that more in the future. Now, if I have any probability distribution, this is our formula. And what we do is we take all of our x2 times our probability 2, our x3 times our probability 3, and our x, and it keeps going till xn times probability of n. We multiply all of those together and we add them up. And this is a really shorthand way of writing it. So it's the sum of all x's times their p's. And that's going to be the mu. It's also called the expected value. And this is something you have to look at. Whenever any question talks about what is the expected number of something, what they're talking about is the mean of a random variable. So expected value is the same as the mean. So here's our definition for mean of a discrete random variable. So if we have our probability distribution, to find the mean, we multiply every x times every p, add them all up, so that's the sum of the x's times the p's. Now, if we want to fill in the probability distribution for all the integers from 1 to 9, if we're just picking random integers, there'd be a 1/9 chance of getting all of these. That's supposed to be a 9. And now if I want to find the mean, I'll do that in a different color. If I multiply this down, this would be 1/9. This would be 2/9, 3/9, 4/9, 5/9, 6/9, 7/9, 8, and 9/9. And if we add up all these top numbers, we get to 45/9, which is the same as 5. Now, if we do that with this thing called Benford's law. Benford's law is a way to see that someone's cheating on their taxes. In order to do that, what we have to do is multiply all of these down and add them up. Take a second and do this on your own. All right, now if you take a second and multiply all these down on your own and pause the video, see if you can find the mean. Well, the values are here, and when I add them all up, I'll get 3.441. So that's my expected value. Notice how this one isn't in the middle. If you look at my next graph, here's two probability histograms. Now this is what we call a uniform distribution. So its median is at the same point as its mean. In this case, since it's skewed to the right, our median would be a little bit to the left of our mean. Because remember, the mean gets pulled towards the direction of the outliers. Now, if we want to find the variance, we take each x value minus its mean squared, multiply it by the probability, and add it up. And then when we square root that value, we find the standard deviation, which is kind of a long process. So we set it up in this situation. What we do is we take each x value, multiply it by its probability first so we can find the mean. Take a second and do this. Alright, so here are some numbers that I got. When I multiply it across, I get 0, 0.39551, 0.52734, 0.26367, 0.0586, and 0.049. Now, when I add these up, I get 1.29. That's our mean, so somewhere around here. Now, if I want to find our variance, what I do is I take each x value, so 0, subtract 1.29, and square that number, so negative 1.29 times our probability, and I get a value of 0.39742. Do the same thing here. This number minus the mean, square it, times the probability, and I get 0.03421. And so on all the way down. And finally, 0.13459. Now when I add up all of these numbers, I will get 1.06, which is my variance. Now if I square root that, I'll get my standard deviation, which is 1.029. So here's our mean, here's our standard deviation, and here's our variance. Now there's an easier way where we type all of these values in our L1, these values in our L2, and we type one variable stats. So on your calculator it just says one var stats, but it means one variable stats. And then we have to type in L1 comma L2. If we don't do this, then we can't find them. So the mean is the x bar, the variance is the one that looks like this. So I'll type these into my calculator. I'll pause it so you don't have to wait for me to type it. Alright, the value of our mean is 1.1 with a standard deviation, and that's sigma of x. That's 0.9434. Now, even though our calculator says x bar, what we really mean is our mean of x. This is how it should be written, but they just use x bar, which isn't what we want. Alright, now this doesn't give us our variance. To find our variance, we have to square this. So to find the variance, I take 0.9433 squared, and to get 0.889999, which is just like 0.8900. Alright. Now if we want to find the height of women between 18 and 24 years old, we can take an SRS of 200 women, and the mean height of these women would be x bar. If we took another sample of 200 women, would we get the same result? We might get similar results, but probably not the same exact result. X bar is an approximation for the true population mean of mu. So mu is what it really is, and x bar is the thing that we can measure. If we increase the size of our sample from 200 to 400 to 1,000 to 10,000, we get closer and closer to our mu. Now this brings us to the law of large numbers. Draw independent observations at random from any population with a finite mean, mu. Decide how accurately we want to estimate our mu. As the numbers of observations drawn increases, the mean x bar of the observed values eventually approaches our mean mu of the population as closely as we specified. It stays that close. So as a drawing, if we have 1 to 5 samples, it might not be near our sample mean. But if we have 10,000 samples, it will be really close, if not right on it. Now I asked what's wrong with this graph, and that was kind of something to have a little conversation about this. 10, 100, 1,000, Notice how this is going up exponentially, so if we log this, it would be scaled correctly. All right, now the law of small numbers isn't really a law. It's saying that we can get hot streaks in basketball, even though the average is 0.5. You could, if your shooting percentage is 0.5, you could get 10 in a row. Um, or hitting streaks in baseball, the same thing. Uh, in a small amount of observations, you won't get your true probability, but in the long run, that's what's going to happen. Our intuition is not reliable in distinguishing random events from systematic patterns. This is why we need statistics. All right, so here's your homework. Good luck.